Section 8b is about doubling time. Let's suppose you have a population of 10,000 that doubles every 10 years. So the first 10 years, you have 10,000. Doubling it is just timesing it by 2, which gives us 20,000. The next 10 years, or 20 years, because it's 10 and 10, gives us 10,000 times 2 times 2, which is the same as 2 squared, which gives us 40,000. The next 10 years is 30 years later, is 10,000 times 2 times 2 times 2 because it doubled again. In this case, 2 to the third power. 2 times 2 times 2 is 8. 8 times 10,000 is 80,000. Do you see what's happening to our exponent out here? 2 to the 1, 2, and 3. That moves us to our formula of doubling time. This is new value is equal to the initial value times 2 being raised to some power. And it's going to be our little t over capital T, with the lowercase t representing the time elapsed, and the uppercase T is the time it takes to double, or the doubling time. Let's suppose you have a bank account that doubles. It has a doubling time of every 13 years. By what factor does your balance increase in 50 years? Now, I could take the whole formula, but I don't need that. It just wants to know the factor. So I'm going to take this portion. What do I multiply to the initial value? So I take 2, raise it to the little t, or the lowercase t, standing for the time elapsed. By what factor does it increase in 50 years? So I'm going to raise it to the 50, and I need my time to double, which was given to us as 13 years. So we have 50 over 13, and I can plug that into my calculator or into Microsoft Excel, and we'll get 14.382. Highlight it as the answer, and answer the second question. For example, if we start with $1,000, after 50 years, because that's how much we are increasing, 50 years, we would have $1,000 times our factor, which would give us $14,382. Our second question, B. The world population doubled from 3 billion in 1960 to 6 billion in 2000. If the world population continues to double every 40 years, what will the population be in the year 2030 and the year 2200 or 2200? So we'll take our equation, new value equals the initial value times 2 raised to the lowercase t, which stands for the elapsing time, over capital T, which is the doubling time. So we need to figure out first how many years from 2000 to 2030. 2000 to 2030 is 30 years. We could also have used our other time, which was 1960, and that would be our 2030 minus 1960, and then we would use our years of 70 versus 30 years, but then we would have to change the initial value to be 3 billion and use our equation with the initial value of being 3 billion for the initial value and the time elapsed of 70. In this case, we're going to use the 30 years just to see. Either way, we will get the exact same answer. So 30 years, my initial value at the year 2000 is 6 billion. So I'm going to put 6 billion in for my initial value versus this one where I would have done 3 billion if I had used my 1960. In this case, I used 2000 to be the initial. Then I times it by 2, raising it to the time elapsed, which is 30 years from 2000 to 2030, over the time to double is 40. Plug that into your calculator or into Microsoft Excel and we'll get 10.1 billion. If I wanted to change the initial value to 1960, which I could have, my 3 billion times 2, it would have been 70 years over 40. And again, I would still have gotten 10.1 billion because it's all relative. All right, the next one for the year 2200. Again, I'm going to have to subtract to find the time elapsed. So 2200, I can pick several different initial times, but just to make things nice, let's go ahead and use the year 2000. So 2200 subtract the year 2000 gives me a time elapse of 200 years. I could have done my 1960 previously, but we're going to stick with just the 200. Now, because I used my year 2000 as the initial, I need the population at the year 2000, which is 6 billion. So I have my new value, here's my equation, my new value equals the initial value. In the year 2000 it was 6 billion, times 2 raised to the time elapsed to get to 2200, it was 200 years, divided by the doubling time of 40, because it's continuing to double every 4 years. Plugging this into your calculator or into Microsoft Excel, you'll get 192 billion, the power of doubling. Roman numeral 2, approximate doubling time formula. This is kind of a rule of thumb. You'll use it in your homework and maybe even a test. Capital T, subscript double. This is the time it takes to double is approximately equal to 70 divided by p, where p is the rate, or p%, of the exponential growth per time period. A. In 2000, the world population was 6 billion, which we got from our previous problem, and was growing at a rate of 1.4% per year. Find the approximate doubling time. So we take our equation, T double is approximately equal to 70 over P. Now this is a little new to see this approximation sign. So those of you who have started with me at the beginning, you know I repeat myself. So I'm going to come up here and just show us how to write T, and I want a subscript. Click here, type in double, get out of the subscript, and then approximately equal, insert, symbol. Mine happens to be here because I've used it. You may not have it really close, so you'll have to go find it in your more symbols. Here it is. Double click, insert. Oh, I inserted it twice. And it's the approximation, approximately equal to, and again, you can go in and do an equation to get your fraction to work out nicely. Using your arrow button over, 70, down arrow, 1.4, because it was 1.4% per year. So I'm going to do per year by highlighting this and giving me another fraction, per over arrow or down arrow, year. Now, oh, my fingers are on the wrong keys, year, over. Now when we divide fractions, you really multiply by the reciprocal, so this per year is really going to flip up onto the top, and I'll get 70 divided by 1.4 gives me 50, and the years are on top, years. So it was approximately doubling every 50 years. Let's go back up and see, what did it say it was doubling? Every 40 years. So it is approximately equal. And I'm going to highlight this because that was the approximate doubling time. Also, please note, and I've made a little comment off to the side, on this one, do not move the decimal. You take the P and just drop off the percent. Let's go ahead and check with the year 2030 just because. 2030, we had new value equals the initial value. in 2030 is 6 billion times 2 to the elapsed time. If we're checking with 2000, it was a 30-year difference. And in this case, our doubling time is 50, where up here we used 40. And let's just see what we get. Type it into your calculator, and your answer is 9.1 billion, which when we did it with the original or the exact doubling time of 40 years, it's pretty close. 9.1 billion versus 10.1 billion. So it's the approximate doubling time formula. Let's move to the next one. The population doubled in 40 years from 1960 to 2000. What was the average percent of growth per year? So we're going to take our approximate doubling time, and in this case we want the percent. So let's solve this equation for p on the bottom. So I need to multiply both top and bottom by p times p, and take this one and times by p. Here it will cross out, but I'm not quite done. I need to solve for p, so now I need to divide both sides. So I'm going to insert another equation just so we can see it, and I have p, and just to speed us up a little bit, I'm going to do just times t. We know it's a capital T, which means t double, and just to speed us up a little bit, equal sign. In this case, I'm only left with 70 on this side, and I need to solve it for p. So I need to divide both sides. So I'm going to change this to a fraction. Divide both sides by t. Now I have one on top and one on bottom. These can both be canceled out. And take this one, also divide it by down arrow, capital T, and now p is solved all for itself. Oops. Click out. There we go. I've now solved it for p, and I have p is approximately equal to 70 over capital T, which is the doubling time. So I was given the doubling is 40 years, and it's 70 for the approximate over 40. Typing it into your calculator or Excel, 1.75% growth per year. And we were given the 1.4% from this one per year, and because it's approximate, that's pretty close, 1.75, comparing it to 1.4. Let's move on to the Roman numeral 3, exponential decay and half-life. Radioactive elements have a half-life, or the half amount of radioactive material after a certain amount of time. Plutonium-239, uranium, also potassium-40 are all radioactive elements. Carbon-14 has a half-life but is not radioactive. This means after a certain number of years, which in these cases are a really long time, it has half the amount of radioactive decay, or radioactive amount present. Plutonium has a half-life of 24,000 years, and so if I were to decrease from 100 pounds after 24,000 years, it would be 50 pounds of plutonium left. In 48,000 years, it goes from 100 pounds times half-life times another half, or 1/2 squared, is 25 pounds. In another 24,000 years, or in this case 72,000 years, it goes from 100 pounds times 1/2 times 1/2 times 1/2, because it's 3 half-lives. I have 24 times 3, 3 half-lives. 1/2 times 1/2 times 1/2, or 1/2 cubed, is 12.5 pounds, which leads us to our next formula. This one is very similar to the doubling, except that this one is new value times the initial value times 1/2 raised to the t over the t of the half-life. This t is the elapsed time, and this is the time that the half-life occurs. So let's go on to the next one. If you've heard of carbon-14 dating, this is what they use. Carbon-14 has a half-life of 5,700 years. What is the fraction of the initial amount remaining after 1,000 years? So I have a new value equals the initial value times 1/2 because it's half-life, t for the time elapsed over t for the time of the half-life. Now I want to know the fraction or the factor of what it's going to be multiplied to the initial value. So I just take this portion of the equation and I have 1/2, raise it to the time elapsed. We were given the question, what fraction of the initial amount remaining after 1,000 years? So the time elapsed is 1,000. The half-life is 5,700 years. 5,700. Type this into your calculator or Excel and we'll get 0.885. And that's the fraction of what we can then multiply. If it had 100, then we can move the decimal over and get 88.5 after 1,000 years. Let's go ahead and take that off. And here's our fraction, so highlight that as the answer. Carbon-14 dating is used on organic materials. So after a certain span, the organic materials will eventually decay and be replaced into things like fossil. And you'll have a fossil bone, which then you'll have to do a different kind of dating. Let's move to the next. Suppose that 100 pounds of plutonium-239, now remember this is a radioactive element, is deposited at a nuclear waste site. How much of it will still be present after 100,000 years? Now remember, we gave you plutonium's half-life is 24,000 years. So we're going to use our formula. In this case, we're going to use the whole formula because we want the final amount. The initial amount was given to us of 100 pounds, and we take 1/2 raised to the time elapsed, which was given as 100,000 years, divided by the half-life of 24,000 years. Typing this into your calculator or into Excel, and since I haven't done it this time, let's go ahead and just copy and paste to show you that we can still use Excel as a calculator. Equals, Control V to paste. Let's see if we have any extra stuff. I'm going to take out these spaces just because I have my 1/2 raised. Everything in here is in the exponent. That's good. The parentheses are in the correct spot. Press enter. Something is not working. Inside here, I think it's going to be that divide sign because sometimes it copies funny. So I'm going to delete. There we go. 5.56. Go back in. And 5.6, which was 5.56 raised to 5.6 pounds. All right, let's move to the approximate half-life formula. Very similar to the approximate double time. This is T sub half-life approximately equal to 70 over P, which is the exact same thing of P% per time period. But this is half-life. Let's suppose that inflation causes the value of the dollar to fall at a rate of 12% per year. Approximately, how long does it take for the dollar to lose half of its value? So we take T, half-life, is approximately equal to 70 divided by 12 per year. Now remember, 12%, you don't change it to a decimal on these ones. And because I'm dividing by a fraction, which is multiplying by the reciprocal, the divide a year, reciprocal means flip it upside down, and years come up on the top. 70 divided by 12 is 5.8 years. Moving on to Roman numeral 5, the exact doubling and the exact half-life formulas. This is using logarithms. That probably scared some of you by saying the word logarithm. A logarithm is just rewriting an exponential equation as the exponent. So you can't rewrite something with the exponent without a logarithm. This is T subscript double equals log base 10. That just means that I'm using the base of 10 and the answer is 2 and I'm looking for the exponent. And again, log base 10 of parenthesis 1 plus r. R is the rate, and so you will move the decimal over two place values when it is given to you as a percent. And the half-life formula, very similar. All right, except the difference here, please note, it's a negative sign out in front. We can still use Microsoft Excel using our logarithms. You can also use your calculator. To use Microsoft Excel to work as a logarithm equals log, and we want to use things in base 10, so I'm going to click base 10. There we go, and then you'll type in the number. In hours it was 2, and then we divided it and so forth. And we'll come back and do some more of those. Our first example. The growth rate of 80% per month means P equals 80 per month, or R is 0.8 per month. What is the doubling time, the exact doubling time? So I'm going to plug everything in. T double equals log base 10 of 2 over log base 10 of 1 plus r. R in this case is 0.8 per month. So it's going to be 1 plus 0.8. You can type this all into your calculator. In this case, let's go ahead and do it in Microsoft Excel. We have log base 10 of 2 over 1 plus 0.8 is 1.8. So we already did the first part, log base 10 of 2. Let's divide it by, again, log 10 of 1.8. Close parenthesis or press enter because it will recognize that we are finished. And there we go. We have our 1.18 or we got 79, which rounds up to 1.8 a month. If we wanted to compare that to the approximate doubling time formula, that's our T double, which is approximately equal to 70 over P. And in this case, it was 80%, which we don't move the decimal on, so 70 over 80 is 0.875 a month, which is pretty close to our 1.18 a month. Let's suppose the value of the dollar is falling at 12% per year. What is the exact half-life time? So in this case, we're going to use our formula of half-life, which has a negative sign. So we have negative log base 10 of 2 over log base 10 of 1 plus r. But in this case, the dollar is falling at a rate of 12% per year. So the falling portion is an exponential decay, and instead of doing a plus sign, we are going to subtract. So I have negative log base 10 of 2 over log base 10 of 1 minus 0.12. I'm going to go ahead and copy and paste this into Microsoft Excel. All right, now you'll notice that it's not recognizing all of the formulas, so we're going to type it or delete these so that we get the log portion. Delete, oops, went too far, log 10. And we have 1 minus 0.12, have our negative sign out front. I'm not sure if it'll read it all. Let's go check it out. Log base 10, oh, I need parentheses around the 2. All right, 5.42, and we have 5.42 years. Compare that to what we had earlier up here of 5.8, which was the approximate. It's rather close. All right, I hope you join me in the next section when we move into loan basics.